You know that golden telescope we humans built that's taking some mind-blowing pictures of space right now?
Well, that's the problem. The James Webb Space Telescope, we may have to rewrite all the textbooks about the beginning of the universe.
More than 2 years after the successful launch of the James Webb Space Telescope, astronomers are now enjoying a fruitful period of discovery as the telescope pushes the limits on what we can see. Yet, these breakthroughs have also unleashed a Pandora's box of puzzles for cosmologists. This is one of the most distant objects humanity has ever observed. It's a single point of light that has traveled for roughly 13.5 billion years to reach the James Webb Space Telescope. This is galaxy JADES GS-Z14-0, seen by Webb at a time when the universe was only 290 million years old. According to our established cosmological models, this galaxy is far brighter and more massive than it should be. In fact, based on the theories of cosmic evolution we've relied on for decades, its existence is a significant puzzle. More than 2 years after its launch, the James Webb Space Telescope is pushing the limits of what we can see, and this single discovery is so challenging that it's forcing astronomers to question our understanding of how the very first galaxies formed. The first chapter of cosmic history is being reevaluated, and what we're finding is vastly different from what our models predicted. For decades, our scientific picture of the early universe was framed by a specific timeline. It began with the Big Bang, followed by a period known as the Cosmic Dark Ages, a vast expanse of neutral hydrogen gas. There were no stars and no galaxies. The prevailing theory, known as the lambda-cold dark matter model, describes a hierarchical process. Small, faint structures of matter were expected to form first, gradually merging over billions of years to create the large galaxies we see today. This was a story of slow, methodical construction. We expected the first galaxies to be dim, small, and disorganized. Then we launched the James Webb Space Telescope. It was engineered with a primary goal: to see the dawn of the first galaxies. Its instruments are tuned to the infrared, built to capture the ancient, stretched light from the most distant objects in the cosmos. And what its findings suggest the early universe was far more active than we believed. In early 2024, astronomers on the jwst Advanced Deep Extragalactic Survey JADES team were analyzing new data when a particular object stood out. In a patch of sky within the constellation Fornax, one candidate for an extremely distant galaxy was unusually bright. Initially, there was skepticism. A bright object often implies it is closer than it appears. To confirm its distance, the team needed to perform spectroscopy. They pointed Webb's near-infrared spectrograph, or NIRSpec, at the object for almost 10 hours. The resulting data was a bombshell. The spectrum revealed a massive redshift, initially measured at 14.32. This confirmed that JADES GS-Z14-0 was being observed as it was just 290 million years after the Big Bang, breaking the previous record. But confirming its age only deepened the mystery. The analysis revealed a galaxy already spanning over 1,600 light-years and blazing with the light of young stars. While small compared to the Milky Way, it is colossal for that early epoch. Its brightness implies a mass of several hundred million times that of our Sun. Our models of galaxy formation simply do not account for building something so large and luminous so quickly. It directly contradicts the idea of a slow and steady formation process. The immediate question for the astronomical community was profound. How can nature make such a bright, massive galaxy in less than 300 million years? To understand the significance of this discovery, we need to understand how astronomers measure such vast distances. The answer lies in two concepts: redshift and spectroscopy. As the universe expands, it stretches the light traveling from distant galaxies. The light's wavelength gets longer, shifting it toward the red end of the spectrum, a phenomenon called redshift. The greater the distance, the greater the redshift. A high redshift means the light, which was once visible in ultraviolet, has been stretched into the infrared part of the spectrum that Webb is designed to see. But just seeing a red object isn't enough. Dust can also make galaxies appear red. This is where Webb's instruments come into play. The process begins with the near-infrared camera, which takes deep images through multiple filters to get a first-pass estimate of distance, known as a photometric redshift. This is how JADE's GS-Z14-0 was first flagged. For a definitive confirmation, astronomers use the near-infrared spectrograph. A spectrograph splits the light from a galaxy into its constituent colors, creating a spectrum, a unique barcode of light with dark and bright lines corresponding to different chemical elements. Near-infrared spectrograph can precisely measure how much this barcode is shifted to the red. For JADE's GS-Z14-0, it measured the Lyman alpha break, a feature caused by hydrogen shifted by a factor of more than 15, which initially confirmed a redshift of 14.32. But that's not all. In March 2025, follow-up observations using the Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile detected something astonishing: the clear signature of oxygen. Oxygen is forged in the hearts of massive stars and released only when they die. Finding it in a galaxy this early is a smoking gun. It proves at least one generation of massive stars had already lived, died, and enriched their surroundings. This ALMA data also allowed for an even more precise redshift measurement, refining it to 14.1793. The galaxy wasn't just forming. A cycle of stellar life and death was already well underway, far earlier than expected. So, what are the implications of finding a galaxy so massive, bright, and chemically mature so early in the universe? It means our models need to be revised. That's not to say the Big Bang is wrong. In fact, this discovery reinforces the core idea of an expanding universe. What it challenges is the timeline that followed. The standard lambda-CDM model predicted a slow, gradual start to galaxy formation, with small halos of dark matter slowly attracting gas to form dim galaxies over billions of years. The existence of JADE's GS-Z14-0 suggests galaxy formation was shockingly rapid and efficient. This isn't an isolated anomaly. It is part of a growing body of evidence from Webb that the early universe was more developed than predicted. Webb has found numerous other unexpectedly massive galaxies and supermassive black holes that seem far too large for their age. This discrepancy has given rise to new distress in cosmology. This has sent theorists scrambling for new ideas. One possibility involves the very first stars, known as population 3 stars. These hypothetical stars are thought to have formed from the pure hydrogen and helium of the Big Bang. Theoretical models suggest that without heavier elements, they could have grown to be hundreds of times more massive than our Sun. Such stellar behemoths would have burned incredibly hot and lived short lives, rapidly producing light and heavy elements. Another, more exotic idea proposes different seeds for galaxies. Some theories suggest the existence of direct collapse black holes, primordial black holes with masses tens of thousands of times that of our Sun that could have formed directly from collapsing gas clouds. These could have acted as gravitational anchors, pulling in gas at an accelerated rate to build massive galaxies almost instantly. The detection of oxygen also tells us something profound. It means the interstellar medium was already being enriched with the building blocks for future stars and planets. The conditions for chemical complexity, which eventually led to us, were being established far earlier than our models had predicted. What the James Webb Space Telescope has done with the discovery of JADE's GS-Z14-0 is more than just break a record. It has revealed a significant discrepancy between our models and observation. We have journeyed back over 13.4 billion years to witness a galaxy from the cosmic dawn. We've seen how astronomers use redshift and spectroscopy to confirm its incredible age. And we've been confronted with its implications. A galaxy that is far too massive and chemically developed for its age, challenging the timeline of our galaxy formation models. This is the essence of the scientific process. A single observation can force us to rethink our understanding of the cosmos. For decades, we theorized about the cosmic dawn. Now with Webb, We are there. We are seeing it. With each new spectrum analyzed, the James Webb Space Telescope shows us that the universe has always been more complex and surprising than our simulations predicted. JADE's GSZ 14-0 is not the end of the story. It is the beginning of a new one, as astronomers are confident they will find even more of these luminous early galaxies. The discovery of JADE's GS-Z 14-0 has created a new dilemma for cosmology. What do you think is the biggest mystery the James Webb Telescope will uncover next? Is it the true nature of the first stars, the origins of supermassive black holes, or something else entirely? Let me know your thoughts. This is Cosmic Chronicles. This is your space. Like and subscribe for more space discoveries.